In this video, we're going to compute the area bounded by the cardioid r of theta equals 2 plus 2 sine theta. So let's take a look real quick at how this thing is plotted as theta goes from 0 to 2 pi. And what we mean by the area of a polar curve is the area captured if we split the curve into infinitesimal sectors like this. Now you might have noticed that the animation started from the cusp, and that cusp occurs at theta equals negative pi over 2, and we can show this real quick by evaluating r of negative pi over 2. And the sine of negative pi over 2, that's negative 1, so I end up with a 2 minus 2, and I end up with r equals 0. That puts us right at the origin where the cusp is. Then our area animation terminated at theta equals 3 pi over 2. That's when we get back to the origin at that cusp. And again, it's simple to show that this works. I plug in theta equals 3 pi over 2, evaluate the sine function, that's negative 1, and again I end up with 2 minus 2, which is 0. So we could set up our area integral this way with limits of integration negative pi over 2 to 3 pi over 2, but 0 to 2 pi will work just as well because the curve is traced out exactly once on that interval as well. It's just that it looks like this instead. So that's just something you want to be mindful of when you're plotting polar curves. For example, if we wanted to get half the area and double the result, it would be wisest to start at negative pi over 2, because when you start at theta equals 0, you're cutting off a little slice at the bottom of the cardioid and it ruins your symmetry. So let's get into the area integral. We start with the formula for the area of a polar curve, and I'll post a link real quick to where this was derived. So 1/2 integral from the starting angle to the finishing angle of r squared d theta, and we plug in our function. And again, there are times where you might want to employ some tricks with splitting up the area and really thinking carefully about the starting and finishing angles. But in this case, it's simple enough to just start with 0 and end with 2 pi. And my curve is 2 plus 2 sine theta. I have to square that, and then I have my d theta. I'm going to go ahead and pull out a 2 out of that 2 plus 2 sine theta, and then it gets squared, so that's a 4. If I bring that out in front of the integral, the 1/2 cancels a factor of 2, and I end up with a 2 there. And we'll go ahead and expand that squared binomial. And the first two terms in the integrand, those are easily guessable, but the third term, that requires a trig identity to knock down the power of the sine function. So sine squared is 1/2 times the quantity 1 minus cosine of twice the angle. And we'll distribute the 1/2 in there as we go. And we'll combine the constants in the integrand. Now we can go ahead and guess the antiderivative of each piece. And 3/2 integrates to 3/2 theta. 2 sine theta integrates to negative 2 cosine theta. And then I have to consider the chain rule in the third antiderivative. The antiderivative of cosine of 2 theta would be 1/2 sine 2 theta. Combining the 1/2 gives me a 1/4. And you can verify that that's correct by taking the derivative of that term really quick, and I would get the cosine of 2 theta multiplied by 2 when I differentiate because of the chain rule. And I get back to what I started with, so that's good. Then I'm going to evaluate on 0 to 2 pi. So instead of just plugging in the numbers with brute force, I want to take a look at these trig terms because often there are things that are going to cancel out. So what I noticed first is that in the sine function, I have the sine of twice 2 pi for my upper limit. That's the sine of 4 pi, and that's 0. In the lower limit, I have the sine of 0, which is 0, so that term is gone. Then in the cosine term, when I put in the upper limit, I get the cosine of 2 pi, which is 1. But I'm going to end up subtracting a term where I plug in the lower limit, and I get the cosine of 0, which is 1. So I know that the upper and lower limits for that term give me the same number, and those cancel out in the difference. The only survivor here is my first term, 3/2 theta, and when I plug in 2 pi for that, I end up with a grand total of 2 times 3 pi. And when I plug in the lower limit for theta, that contributes nothing. That's 0. So that's gone too. So in the end, we come out with a total area of this cardioid of 6 pi. And we're done. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.